For this next video, I thought I would just include a quick discussion of end behavior in general. And we'll start the discussion off with polynomial functions. So start this off with a claim. Here's a very large polynomial function, or a lot of terms I guess I should say, f of x, and then a much simpler one, g of x. I claim that these two tend to the same value as x goes to either positive or negative infinity. So what I mean by that is when x is very large, all of these other terms here become insignificant. Saying this another way, if I were to divide these two limits, you ought to get 1. So to prove this to you, you need to recall these two facts from the previous video. So right now this is the question that I'm trying to answer. So what I've done here then is I've combined the two into a single limit, and I have split these up into separate fractions. Now in this step what I've done is I've taken this first term and simplified it, and I've taken the second term and I've written it so that it's three separate things. So so in that sense, what I've tried to do here is show you that as x gets very large, we can go back to our two facts from before and realize that this is going to go to 0, and so is this. And you can do that basically the same way for all of these other terms. So now you have 1 plus a bunch of zeros, so the limit as x goes to infinity of 1 is 1. So what this is meant to show you is that if you're looking at the graph of a polynomial function on its extreme ends, the only term that matters is the first term. Alright, so you can basically do the same thing if you pick negative infinity. The proof works exactly the same way. Alright, so just a quick example to show the power of what we just did. So we've got this pretty nasty looking function f of x, and we want to determine what the end behavior model of this function is. In other words, what does this graph look like on its extreme ends? So basically the numerator, as x gets large, the numerator tends to x to the 6th. The denominator tends to 3x to the 7th. And so 1 over 3x is a nice simple end behavior model for this function. So what this means is that you can look at the graph of y equals 1 over 3x, and you get a really good idea of what the function f is doing. Just a quick graph of 1 over 3x leads you to see that it's something like this. And so even though they didn't ask for this, we could say that there is a horizontal asymptote at y equals 0. Alright, one more example and then we're going to wrap this up. So here's another rational function. We're going to do the same kind of thing. So looking at the numerator of this function, the numerator tends to x to the 6th, the denominator tends to x to the 4th. If we divide those two, we get x squared. So what I'm saying is that this function looks no different from x squared for very, very large values of x. That might be a bit of a surprise to you. So to try to convince you of this, I'm going to try to graph this as well as x squared. Okay, there we go. Okay, here are the two graphs in a standard window, negative 10 by 10. Again, close up, they don't look anything alike at all. But if we zoom out quite a bit, if I set my window up like this, look what happens. Okay, there's the... Well, they're kind of close together. Let me try to tighten up x a little bit. Alright, I've actually decided to make y larger. Let's see what that does. Okay, much better. So that first one was g of x, and x squared gets graphed right underneath it. So again, the point of the exercise is to show you for very large x, this rational function looks exactly like x squared.